Okay, welcome to class meeting 28 of EECE574, the graduate level probability and random processes. The final exam will be taken next Wednesday at 7 p.m. at the next classroom. Topics of voluntary projects must be determined before you take the exam, and you must be confirmed by me about the topic. You cannot arbitrarily choose the topic. Overview is like this. We are working on these systems with stochastic inputs. And unfortunately, since this is the last class meeting of this semester, we will not be fully covering the power spectral density parts. Fortunately, I've been teaching this part for a long time and have a KMOOC lecture if you want. And also, if you go to one of my teaching website, especially 575, which never been taught. But anyway, if you go to this link, then from here, you can find all the PDF files and the link to the KMOOC lecture. So you don't need to log into KMOOC site to see this one. You can just go to this site and click the buttons, then you can see the PDFs and also videos. So I strongly encourage you to study this material if you are in digital communications area. Okay, anyway, so let me continue. So we were here. There are many systems we need to handle as an electrical engineer, especially a communication engineer. Mostly they are linear, but not necessarily linear time invariant. So we need to handle linear systems. And also sometimes we have to handle nonlinear systems. There are many types of nonlinear systems, but one of the most important nonlinear system is actually almost linear, in the sense that its input and output relations are described by a linear constant coefficient differential equation. And some of you say that, wait a minute, if a continuous size system's input output is described by a linear constant coefficient differential equation, this must be an LTI system. You are partially right, but you are not fully correct, because linear constant coefficient differential equation may have zero input response in the case when you have initial non-zero initial condition. So you must be careful. Second type of nonlinear system is a memoryless nonlinear system, where the output is directly a function of an input. That kind of memoryless nonlinearity is not actually occurs in the real world, but in some cases we model a system in that way. For example, given a nonlinear power amplifier, there is a model, approximate model, where the output amplitude and output phase of the bandpass signal is just determined by the input signal at the same instant, something like that. But when I asked about the accuracy of that model to some professors in amplifier design, they say that that is an approximation. So anyway, there are many cases where power amplifiers are modeled by memoryless nonlinearity. So that is also you need to remember. But anyway, we are not going to delve on it, that kind of memoryless nonlinearity in this course. We are just focusing on today the possibly nonlinear system with input-output relation described by a linear constant coefficient differential equation. So this is the input-output relation, where x is the input and x sub L is the L, so the derivative of the input. Also, you have y and y sub k, which is the output, and the case for the derivative of the output. Here, you have to be careful in the sense that your sum is a finite sum. So you only have a finite number of terms. Here, there are n terms, and here there are, let me see, something's wrong, just a second, from 0. So you have, on the right side, you have n plus 1 terms, including the original x of t that is represented by x sub 0 or just x, and also the output y sub 0 or y. So there are m plus 1 terms on the left-hand side and n plus 1 terms on the right-hand side. Both m and n are finite. If either m or n is infinite, we usually do not call this linear constant coefficient differential equation. Okay. Anyway, so given this input and output relation, as I just told you, this system is in general not linear at all. Okay. However, if it is linear time invariant. But anyway, given that, our problem is what? Since the system is described by an LCCDE, what we want to know is the output characteristic given the input characteristic and the LCCDE. Unfortunately, it is very difficult to fully characterize an output of even a linear time invariant system given the total full description of the input. There are very rare cases where you can do that. So we are just interested in computing the second order moments of the output most of the time. And also, it is quite useful if you are interested in computing expected value related output. For example, as I told you, probability of output to be greater than or something can also be rewritten as the expectation of something. So we just compute the mean and autocorrelation function of the output in this case. So the problem is this. Given the LCCDE and given the input, mean, path, and autocorrelation function, what is the mean, path, and the output autocorrelation function? Got it? Since the problem is quite complicated for general m and n, we just focus on the case where n is 0, which means that we only have a single term of the input, where input is not differentiated at all. So by dividing both sides by B0, we may have some m plus 1 terms here and just single term x of t. That kind of model, a special case model of LCCDE, is called the autoregressive model, AR model. And if we just call the number of the highest differentiation as p, that model is called ARP model. Got it? So we just compute the we just learn how to compute the mean, path, and the autocorrelation function of the output in ARP model. Okay? You can extend this idea for any ARMA model where you have here this becomes P and this becomes Q, something like that. Okay. Anyway, so we start from this model. So we have just a single x of t, and here you have y over t multiplied by a0, y prime of t multiplied by a1, and his order derivative of y multiplied by a sub p. Now, we divide our approach into two cases. First, we have general x of t. Here means that general means it's not necessarily y-sense stationary. And the other is the special case where x is y and stationary. So let's do this first. Surprisingly, this general case is simpler. So let's see. So first, we want to compute the output mean pass. How can we find it? The idea is simple. Given this input-output relation, we take the average of the left-hand side and the average of the right-hand side. Here, average is the ensemble average. So ensemble average of x of t is what? Mu sub x of t. So we have mu sub x of t. This is mu sub x of t. And we have expectation of the left-hand side. And here, if we assume under certain conditions that the expectation and the derivative can be interchanged, then what happens? We can rewrite the left-hand side as summation a sub l and the nth order derivative of the output mean path. Then what do we have? Actually, we have a differential equation to solve. It's like you want to find mu sub y of t given mu sub x of t. This is given. And mu sub x and mu sub y are related by this differential equation. And if so, by the way, if mu sub x of t is not that strange function, then actually this differential equation can be very easily solved. By using what? You can use Laplace transform if you want. And there are many other methods to solve this ordinary differential equation. So you can find it basically. Probably you learned how to solve this differential equation in undergraduate calculus course, or in your linear circuits theory course, or your automatic control theory course, or if you have taken my course, my signal gen systems course. So basically, it's not difficult to solve that one as far as mu sub x of t is not that strange. Got it? And the second problem is to find the autocorrelation function of the output process. How do we solve it? It has two steps. The first thing is that we find r sub xy or r sub yx first. And then we find r sub yy. So in order to do that, we take a look at this relation again, and we replace t to t sub 2 first. So here, the derivative is with respect to t sub 2 as I've written. So t sub 2, t sub 2. And then you pre-multiply x of t sub 1 to the both sides. Got it? Then what we do is that we take the expectation again. So if we take the expectation, then what do we have? We have summation a sub l and the cross correlation between x and y because we pre-multiplied x of t1, and here we have y of t2. Got it? So to the differential equation, we multiply x of t1 and change t to t sub 2, then take the expectation. We have this equation. And the right-hand side is given. Even though it is a two-variable function, we assume that the mean pass and the autocorrelation function of the input is given. So this is given. And what we want to find is r sub xy. And here, what is this one? This is simply the nth order partial derivative of r sub xy. So here, this is given, and we want to find the cross correlation. And you may say that, hey, how can I solve it? There is a simple way. You assume T2 is fixed, and then this problem is nothing but this type of problem. So you solve the problem using, for example, Mathematica or some other tools. So let's assume this is now given. Then what do we do? What we do is this. So here, since we have r sub xy, we need some r sub xy. So to this one, let's change the variable to just a second. Yeah, T1. Let's see. Just a second. Yeah. So let's keep this variable as T2. Okay. And what we do is that we multiply y of t. This is not true. Just say xy. Okay. So here we have L a sub L y sub L t equals x sub t. So what? Since we have this one already, we are multiplying y on the right side. So let's keep it t1, and we multiply yt2 to both sides, and then we take the expectation. Then what do we have? Now, left-hand side is the summation of the partial derivative. It would be summation of the partial derivative of the output autocorrelation. And the right-hand side will become the cross correlation between input and output, which we have found already by solving this one, right? So given the input autocorrelation, and of course mean pass, what we find is first the cross correlation function and the output autocorrelation. In that way, we can solve the problem. If you want to study more about this system described by linear constant coefficient differential equation, or sometimes a discrete time system described by a linear constant coefficient difference equation, then there are plenty of materials out there. It's usually an advanced graduate level course in electrical engineering and control, especially. And another one is, interestingly, the business school. They study so-called the analysis of sequence, because in Korean it is called the 시계열 분석, and they really need that to make a financial decision. And before making the decision, they want to analyze what's going on in the market. So since their signal is usually a discrete time signal, they model the system as a linear constant coefficient difference equation based system. In that case, even though they do not have differentiation, they usually have delayed component. So they use Z transform, as we learned in signal and systems and digital signal processing, and do almost the same thing. They are interested in the output autocorrelation, and they are interested in input-output autocorrelation, and they do exactly the same thing, and you will be surprised to find that. Anyway, so let me just stop here for this topic and move to a more complicated topic. In electrical engineering, especially in control and communications, we are interested in modeling a system with many, many inputs and many, many outputs. In very old textbook, this system is called multi-channel system. And the remains are still there. For example, suppose you purchase a data acquisition board, and the input and output is labeled as channel. If you purchase a signal generator, also input outputs are labeled as channel. So that channel is kind of classical term. Got it? And some non-electrical system people named that as multi-terminal system. But as you know, for example, as a computer engineering student, terminal means some dummy terminal or something. So electrical engineers usually use in old cases, use the multi-channel system. There are many input channels and many output channels, but they decided not to use that. And gradually, the term changed to multiple input, multiple output system, even though it's still confusing. For example, suppose you have a single vector valued input and single vector valued output. Is a single input, single output system or a multi-input, multi-output system? Suppose you have a complex valued signal in, complex valued signal out. Is it a single input, single output system or multi-input, multi-output system? Because a complex valued signal consists of two real valued signals. So this multi-input, multi-output terminology is not that precise, but here I'm going to use this MIMO system in the sense that input, whether it is a real valued or complex valued, consists of more than one continuous time signal, and the output consists of more than one continuous time signal. Got it? So input may have 3 complex valued signals and output may have 5 complex valued signals. Given that, if you have taken some linear systems theory course in your graduate program, then you know the linearity assumption of this MIMO system gives you what? The input-output relation given by this. Just a second. This is always confusing. Given by this integration. So similar to a single input, single output linear system, there exists a 2-variable function called the impulse response. But this is a matrix valued. So given t and tau, you have a matrix. So matrix valued function of 2 variables. And you multiply input signal and you have the output. This is a kind of linear system theory approach, but in communications, unfortunately, due to some reason, we usually love this expression. So in order to differentiate this equation with that one, let me use R, that is more like received signal in communications, and S, that is more like sent, transmitted signal. So in communications, we rather use this expression. So actually, this h of t tau would be different from this h of t tau. So let me just use C in that case. Okay. So this is linear systems theory impulse response. The response at time t to the impulse applied at time tau. This C of t tau would be the impulse response of a wireless channel, where t represents the instant at the output and t minus tau represents the time when the impulse is applied. But anyway, since our textbook's author, Populist, was not a communication guy, so he used this expression to expand the results. So this is in general linear system case. And if we restrict by imposing time invariance, then we have input-output relation more familiar. And due to the time invariance, there exists a single variable function, h. Then you may write it this way by using the convolution integral. Okay? So this is a generalization of your ordinary convolution of 2 continuous time signals. Now you have a matrix valued signal and vector valued signal convolved to generate the vector valued signal. Now, given this model, either for general linear system or a linear time invariant system, what you want to do is to repeat we have just done. So given the input characterization. What is the output? You want to characterize the output fully in some cases, or at least partially, finding the mean, pass, and the autocorrelation function. The problem is that since the input is vector valued and the output is also vector valued, we have vector valued mean pass and matrix valued autocorrelation function. Fortunately, we've studied that already. So here goes the special Y-sense stationary case, because non-stationary case is kind of straightforward. It's a kind of simple, straightforward extension of what we just said. So given mu sub x of t, that is defined as the mean pass of the input vector. So given that, and also given the input autocorrelation function. So here it is defined as x of t1 times x of t2 Hermitian transpose. If x is a complex valued vector, so x has its element as complex valued signals. You need to put conjugation here on the right hand side. So what is this given t1 and t2? It's the column times row, so you have a vector. Got it? If Y-sense stationary, what does that mean? You have a single variable function of t1 minus t2. And as we've done, we introduced the parameter tau, which is t1 minus t2. So we have this. Got it? And you can easily show that if input is Y-sense stationary and system is LTI, then output is also Y-sense stationary, which means that you can easily find the mean and easily find the autocorrelation. So let's see. So what we want to show is that the mean vector is a constant vector for all t, and the output autocorrelation function of t1 and t2 is simply a function of t1 minus t2. To show that, let's start from the mean pass, which is expectation of y. And if you just expand that convolution, then what do you have? You have expectation of the ijth element of the matrix value, the impulse response, convolved with the jth element of the input for the jth element. And then if you change the expectation, order of expectation and convolution, then you simply see that the mean pass is the convolution of the impulse response and the mean pass of the input. So that's not a big deal. And similarly, what you do is you take the outer product of the output and take the expectation. And then if you follow the similar process, then suddenly you have something similar to what you've seen last time. So output autocorrelation is what? The input autocorrelation pre-convolved with H of T1 and post-convolved with H of T2 Hermitian transpose. This is what you've seen last time, actually. Just reduce X and Y to a single variable, a single scalar valued function. Then this is H of T1 convolved with R sub XX T1 and T2 convolved with H of T2 conjugate. Got it? Similarly, you can find cross correlation function in this way, and also cross correlation between Y and X. No difficulty. Got it? So even you can expand this idea by considering a MIMO system whose input and output described by a linear constant coefficient differential equation. No problem. Got it? So, okay, here goes the last topic of this semester's probability and random process. The title is the power spectrum. Power spectrum itself takes more than 2 weeks to fully describe, especially for communication engineers. first we are going to introduce the notion of power spectrum first. And finally, finally, we consider the power spectral density of a real valued bandpass signal. Because for communication engineers, the most important signal and process is what? Real valued bandpass process and signal. Because we handle radio wave, and in order to effectively generate radio wave by using electrical system, we use antenna and we apply what? An electrical signal that is better well modeled as a real valued bandpass signal, so-called RF signal, right? So we need to study not just the baseband random process, which may be real valued or complex valued, but we also need to deal with real valued bandpass random process. Unfortunately, we don't have enough time, but fortunately, I have been teaching that part for a long time. And as I told you, we have KMOOC lecture on digital modulation and power spectrum. And also we have the material linked to one of the website in my homepage. So anyway, the topic is very consisting of many small topics, but I'm going to cover it very fast today. The first thing is the difference between so-called energy spectrum and power spectrum, or energy spectral density and power spectral density. What is that? So let's start from a deterministic signal, x of t. And let's define capital X of f as the continuous time Fourier transform. Some of you may say that, okay, I'm more Laplace transform guy, so let me define capital X of s as the Laplace transform of x of t. And then since Fourier transform is the case where s is j omega, then let me use x of j omega as the Fourier transform. And since omega equals 2 pi f, let me use capital X of j 2 pi f as the definition of continuous time Fourier transform used by communication engineers. So sometimes, including me, people use this complicated notation. However, I'm not going to use it in this lecture note. So precisely speaking, this would be correct if you have started your definition of Fourier transform by using the Laplace transform. But let me just simply use x of capital X of f. Got it? Now, under certain conditions, like square integrability, you may have a very amazing result. What is that? That is your energy of the signal defined as modulus squared integrated over the entire real line. This is defined as the energy of x equals what? Equals that Fourier transform modulus squared and integrated. And this relation, as you learned in undergraduate signal gen systems, is called Parseval's relation. But you have to remember this. This relation holds when this energy is finite. Means that when you deal with a finite energy signal. Got it? So given a finite energy signal, you have this relation. The problem is this one. Actually, that is also a white lie. It's not totally a lie, but it's a white lie. Because whenever we define something, use integration, this thing you just defined may not exist. Sometimes what you just have defined by using an integration may not exist in the sense that it may not be well defined or it may not converge. Okay? For example, let me consider something like this. Suppose x of t is what? Delta function squared. And what happens? Delta function squared. Then if you compute that one, then you have, I believe, infinity or something like that. Okay. So for the existence of the Fourier transform, we need, it is, precisely speaking, it is sufficient that x of t is absolutely integrable, which means that, see that the existence of CTFT is not guaranteed in general, but if absolutely integrable, then the Fourier transform exists. So it's like you have the set of all continuous time signals x of t. Then you have so-called absolutely integrable signals subset of absolutely integrable signals. If your signal lies here, then you can compute the Fourier transform defined by this one always. However, if your signal is not inside this subset, you don't know. Okay? Another thing is that here is square integrable function set. And unfortunately, there is no inclusion and exclusion property. This set has some intersection, but not completely included, something like that. But as I just told you, in electrical engineering, in many cases, we assume energy is finite. And because that is physically meaningful, we can never have infinite energy signal. If we are free of power hungry, right? We have infinite signal, and then we may distribute that to every human being on Earth, and no problem. But the trick is that we use infinite energy signal to make our mathematics simple. For example, Dirac delta function. That is very, very useful when we handle electrical signals, conceptual. So it's like, even though the signal is not an impulse signal, delta function, we use that model for simplicity. For example, suppose you have some cascade of serial interconnection of signals. Anyway, eventually you may have some bandpass filter. So your signal content outside that band will be removed. In that case, what you do is that for simplicity, sometimes here, when you add noise, you model the noise as a white noise with power spectrum just flat. Means that, as we learned today, if the power spectrum is flat from negative infinity to positive infinity, its energy is infinity. But anyway, it will be filtered out by this filter. So for simplicity, we say that this is additive white Gaussian noise, something. Got it? So let me repeat. No infinite power signal exists. No infinite power random process exists in reality. However, for mathematical abstraction or simplicity, we use that kind of signal. But never forget that that is an approximation as just for convenience. It never exists. But anyway, so we are interested in sometimes the signals with finite energy signal, but not always, as I told you. Sometimes we need some strange signal. One good thing is that delta function that is not square integrable, that is absolutely integrable, right? So that's good in the sense that we may Fourier transform delta function. Okay. What about these signals that is not absolutely integrable but square integrable? It may not have Fourier transform. But we want to do some frequency domain analysis. So people modified Fourier transform. In what sense? In this sense. Limit delta tends to infinity, negative delta, positive delta, x of t e to the negative j 2 pi of t dt. And you may say that, wait a minute, they are the same. No, they are not. Okay? Probably you remember from your undergraduate probability and random process courses, given a Cauchy distribution, that density is what? That is kind of a scaled version of 1 over 1 plus x squared. So your density function looks like a little bit similar to Gaussian, but it's not. Gaussian has very light tail because it has e to the negative x squared. But this Cauchy distribution has what? Heavy tail. It has 1 over x squared type tail. And probably you remember that many people say that the mean of Cauchy distribution is not 0. And you may say that, wait a minute, it's symmetrical with respect to y-axis. Then definitely mean is 0. Actually, it is not. Okay. Precisely speaking, that integration to compute x times the density does not converge. But if you just approximate your integration using a finite integration, that is called so-called definite integral from positive delta to negative delta. Then, given any finite delta, the value is 0, the kind of mean, approximate mean is 0. And if you increase this interval, then it is still 0. In that sense, its mean may be set approximately or claimed to be 0. Similarly, we may replace this definition of just possibly Lebesgue integral to this integration. And amazing thing is that for square integrable signals, if you modify Fourier transform's definition to this one, there exists some limit of this integral when you let delta tend to infinity. And that is called what? That is called Fourier Plancherel transform by some people. Okay. Even if you take some Fourier analysis textbook from the bookshelf of the library, they never talk about Fourier Plancherel transform. However, there are some mathematicians. They define Fourier Plancherel transform. And actually, Fourier Plancherel transform is what we learned in our signalization systems. We just handled Fourier Plancherel transform, but simply called it Fourier transform. Okay. Anyway, so remember this. Given a square integrable function, when you define energy and when you say Parseval's relation, actually your integration is this one. Got it? Not that one. And if you really want to find the difference between this integration and that one, I suggest you to take a measure theory course. Okay. Otherwise, it's very hard to understand the difference between them. Okay. Anyway, see the Lebesgue integration. This is Lebesgue integration, which means that you need to know what is Lebesgue measure. Okay. Anyway, so as I told you, this is Fourier Plancherel transform. Then you have possible Plancherel relation actually. Now, what's the implication of this one? This is very, very interesting thing. See that? You want to compute the energy of the signal, and you can alternatively integrate something in the frequency domain. By the way, how can you interpret this modulus square of x of t? Then maybe interpreted as some instantaneous power of x of t at time t. And then you integrate to get an energy, right? or infinitesimally small, how to say that, small energy fraction. So it's like, let me retract that statement. This is a kind of x of t squared delta I. So if you replace this one to a summation, then this is a kind of energy contained in a small interval in the time domain. What about this? Let's interpret this one as summation of capital X of f sub I times some interval. That is what? Fraction of the energy contained in this interval, right? And what was the name in your classical mechanics when you integrate and some non-negative function and get a mass of the, for example, object? You call it a density function, right? So you integrate density of mass to get a mass, right? So here you integrate something to get energy. Then you may say that this is an energy density in the time domain. And what about this? You integrate this one to get an energy. You call it density of energy in the frequency domain. And in the frequency domain, that is often replaced by spectral or spectrum, right? So we may say that this is energy spectrum or energy spectral density. Got it? So let me skip this. And so this is called the energy spectral density given a finite energy signal x of t. So you find the Fourier natural transform of a finite energy signal and then take the magnitude square of it and call this an energy spectral density. And this also appears because of this reason. Suppose you have a bandpass filter with center frequency f0 and negative f0 and bandwidth epsilon. And suppose you apply for simplicity, real finite energy signal. Let me just parameterize output for this f0 and epsilon, okay, t. So when the bandpass filter has passband center frequency f0 and bandwidth epsilon, let's call the output as y f0 epsilon. Now, let me ask you, what is the output signal's energy? So what is the energy of your output signal? And you know that input-output is related in this way. Let's call the impulse response of the bandpass filter as h of t. Then what? Your output has Fourier transform that is simply the multiplication of the Fourier transforms of the input and impulse response. Now, in order to compute the energy, what do? You take the energy spectral density of the output and integrate. And to do so, we take the modulus and take the square. And what do we have? Since if energy spectrum of input is smooth enough, this is well approximated as x of f0 squared. Let's assume the height is 1 times the epsilon for this interval, okay? And 0 for other values. So if you integrate, in the frequency domain, what do you have? You have something like this. So approximately your output is the input energy spectrum evaluated at F0 times 2 epsilon. Now, you just make the epsilon small enough and divide by epsilon, then what do you have? You may say that, okay, this is the energy spectrum of the input. Okay? So due to this reason, our justification of calling this one as energy spectrum makes sense. Energy spectrum at frequency F. See that? Energy spectral density at frequency F equals F0. And this interpretation is repeated when we study the power spectral density of a random process, and as you will see. Okay. Now, let's move to a random process case. Let me skip this. Anyway, you'd better study later. Okay, just a second. Okay, so now consider a deterministic signal that has infinite power. Of course, you may say that, hey, you just said there is no infinite energy signal, but you just said, let's consider a deterministic signal with infinite energy. And as I told you, it's for convenience. In your circuit theory course, especially when you analyze the power network, you just assume your signal is a cosine function, right? And ideal cosine function has what? Infinite energy. You square and integrate, that blows up, right? So now you know that everything is approximation. But mathematically, we need to find a way to handle that. So we extend the idea of energy spectrum to a power spectrum of a deterministic signal. To do that, first, we need to define a power signal. First, what was the energy? Energy of the signal was defined in this way. What is the definition of a power? Power of the deterministic signal X. That is defined using time average. So you have some delta that tends to infinity, and you have interval, and then you compute the energy of the signal. The difference between this one and that one is simple. You may rewrite this one as what? As something like this. So here you can clearly see the difference. Okay. So when you compute the energy, you just compute the square of the integration of square. When you compute the power, you divide it by what? The time of the period. So if the unit of this one is joules, then what do you have? Joules per second. That is watt, right? Watts. So this is called the power of the signal. Then let me ask you a question. What if x of t has finite energy? Then what would be the value of the power? 0, right? Because since this with 1 converges, this with 2 delta that blows up would converge to 0, right? So a finite energy signal has 0 power. Then let me ask you another question. Suppose your signal has infinite energy. Then does it have a finite power? Unfortunately, that is not true. So if I draw a Venn diagram, the relation is like this. here is the set of all continuous time signals. And here is your energy signal, which may mean that the energy of the signal is finite. However, usually when we say energy signal, we exclude the signal with zero energy. Okay? Similarly, when we define a power signal, we define it as a signal with a finite non-zero power. So in that sense, we have something like this. What about other thing? It may have infinite power. Okay. Now, given that, how can we describe the distribution of the power of this power signal in the frequency domain? Because we've done something similar to an energy signal. Okay. For an energy signal, we had what? X of t and capital X of f, right? If you integrate this one in the time domain, you have the energy. If you integrate this one, called the energy spectral density in the frequency domain, you have the energy. Now, you have power signal, and you integrate this one. And by the way, what is this one? Have you seen something similar? This operation is what? Time average, right? And we introduced this notation already. Got it? This bracket, right? That is time average. So time average of the instantaneous power is the average power. This is average power. Okay. So what do we have? Actually, we have the same thing, but anyway, what do we have here? And that is related to the so-called power spectrum. Okay. So we have an energy signal, and we have energy spectral density. We have a power signal, we have power spectral density. And if we integrate the power spectrum, then we have the power. Now, let's see an example then. Suppose x of t equals cosine 2 pi f0 t. Then what is the power of this x? By the way, the reason why we put x twice is that sometimes we need to define cross power of x and y. Okay? So if we have cross power between x and y, denoted by piece of xy, and if y equals x, then it becomes the power. And this is the right notation. Got it? That is, this is kind of very similar to the idea of defining our autocorrelation function and cross-correlation function. Now, what is your intuition about this? You have x of t, that is cosine 2 pi f0 t. And you know what is the power. What is the power, average power of cosine function? What is the average power? 1/2? Is it right? Right? It's 1/2. Now, what is, so this is 1/2. And what would be some called power spectrum? Let me use capital S, spectrum of deterministic signal x. And the reason why is that this is kind of auto power spectrum. What would be power spectrum of this deterministic signal? You know from your analysis of Fourier transform in signal-gen systems, you, without hesitation, have written the Fourier transform of cosine function as this one. Let me ask you, is it correct? Actually, This is not correct because x of t defined as cosine function is not absolutely integrable, is not square integrable. Okay? It is so Fourier transform does not exist. Right? And even the Fourier Plancherel transform does not exist. Then what do we do? This is very important signal. So what we do is that we use Fourier Plancherel transform. So we restrict our integration interval to plus minus capital delta and compute the kind of approximate Fourier Plancherel transform and let delta tend to infinity. And we have the generalized function. Got it? So this simple result you learned in signal-gen systems actually has very complicated history. This is not precisely speaking Fourier transform. This is not Fourier Plancherel transform. It's a kind of Fourier Plancherel transform like result relying on a generalized function. But anyway, if, for example, I teach signal systems in this way, probably no one will remain in the Department of Electrical Engineering because signal systems is the second grade course. But anyway, so we know that anyway, the signal component is concentrated at plus minus f0, right? So, and also in other frequency component f, then plus minus f0, there is no content at all. So again, our power spectrum must have something like this. Then what would be the coefficient multiplied by this one? We know that if this power spectrum integrated over the entire period, we must have 1/2. And here we have 1/2. Okay, that squared is related to the energy spectrum. So let me just boldly square this one and put it here. So we want some definition that must result in the power spectrum of cosine 2 pi f0t to that one. What is that? So what people have done is this one. They just boldly, where is it? Yeah, boldly considered this quantity. What is this one? This is simply the Fourier Plancherel transform of x of t truncated to the interval plus minus delta. Okay. Now you have capital X sub delta of f. Got it? And you may say that, okay, what is this? This is the Fourier Plancherel transform of the truncated version of x for finite interval. And as far as this truncated version of x is a finite energy signal, we have well-defined Fourier Plancherel transform. Now, what about taking the magnitude square of this one? Then it becomes the energy spectral density. The problem is that if x is a power signal, if you just let delta tend to infinity, this will not converge. So what you do is that, okay, let me just divide by the interval so that I have some unit that is related to power. As I told you already, suppose this x square has x squared times t, okay, has some unit joules. And if you divide by 2 delta and limit, delta tends to infinity, then you have sec, so you have watts, right? In the frequency domain, you must divide by time to when you integrate this something spectrum and to have power, right? So this makes sense in the when you take the units into account, right? And then we define this one as the power spectrum. And you can easily check by using this cosine function that if you define the power spectrum in this way, then amazingly you have one force, this one. Got it? So it seems this definition for power signal as a power spectrum makes sense. Okay? And you can also do this. For example, suppose your x is the summation of a sub l and e to the j 2 pi f sub l of t, l from some 1 to capital L. So you have what? You now have capital L complex sinusoidal signals with coefficient a sub l. Then you can easily show that your power spectrum of x, this deterministic signal, is what? Sigma L from 1 to capital L, A sub L magnitude squared times delta of F minus F. So actually, this is what? This is a special case of this, where you have only two terms with the same coefficient, 1/2. And F1 and F2 are what? F0 and negative F0, right? And then what happens? Since this is 1/2, if you square it, it becomes 1/4, and you have delta functions. Got it? So you can show this. Now, okay, we have defined the power spectral density over deterministic signal. But it seems whenever we want to compute this one, we need this integration after truncation. Can we have something simple? And that is the motivation of the Wiener-Khinchin theory. Okay? Actually, I remember is that Khinchin did this, and Wiener's result is related to the power spectral density over random process. So it is called Wiener-Khinchin theorem. But if I skip this derivation, interestingly, this right-hand side can be written in a very strange form. That is what? Hey, why? Why computer does not work? Okay, is it time to close? We have 5 more minutes. Hey. Okay, it works, but why our mouse does not work? Strange. Okay, so let me move down. How? Okay, let me use keyboard. Okay, keyboard works. Oh, okay. Just a second. Yeah, okay. This is the power. Where is the definition? Where is Khinchin's theorem? Okay, okay. Let me just write down. So you can show that given a deterministic signal, not a random process. Okay. So theorem, given a deterministic power signal, x of t, the power spectral density S sub x of f can be alternatively found this is not definition, as Fourier transform of time average. Sorry. Something like this. And you may say that, what? First, this F means continuous time Fourier transform. However, it seems there are two variables. So sometimes, let me write down which variable to be averaged or computed for the integration in the Fourier transform, tau. Okay. What about this A? A is time average with respect to t. Okay. So if I rewrite, you have this one, limit delta tends to infinity, and you have 1 over 2 delta. And here you compute this time average with respect to t. First, you compute this one. Then, what is this one? This is a function of tau because you integrate over t. Got it? So this becomes a function of tau, and we often write it as r sub xx of tau. Okay, and then you Fourier transform it. So you have e to the negative j to pi f tau d tau. So this is the theorem by Khinchin, I remember. And you can show that this Fourier transform of time average of the product of x of t plus tau and x of t conjugate is same as what? Same as this definition of the power spectrum. By the way, this one makes sense. You truncate and compute the energy spectrum, and to make the unit convert it to power, you divide by t, time, right? So this makes sense. And when you really use, for example, FFT or in general DFT in your scope, actually they do this. They take a chunk realization of even a random process, then they compute the magnitude scale of the Fourier transform, that is magnitude response squared, and then properly divide by their observation window and show you. Okay, so this is really useful, and you need to remember, because this is very practical. It just makes sense, right? This is energy spectrum divided by time, so you may say that this is an approximate power spectrum. And if its limit exists, I want to call it the power spectrum. But in most of the cases, you want something that is easy to compute. So what you do is this one. You compute the deterministic autocorrelation function of the signal and just apply the Fourier transform. The reason why I have spent today's lecture describing the energy spectrum and the power spectrum of a deterministic signal is that if you look up many other textbooks, there are good explanations and descriptions about the power spectral density of a random process. However, most of them do not talk about this kind of preliminaries. So as far as you have learned now what is the energy spectrum of a deterministic signal and what is the power spectrum of a deterministic signal, then it's not that difficult to fully understand what does that mean by a power spectral density of a random process. For example, this theorem is a definition. This was the definition, right? can be extended for a random process. So it's like, as you see here, so here goes the definition of a power spectral density of a random process. What is that? What you do is almost the same. You take the limit, and here you take the expectation, ensemble average of the magnitude square of the Fourier transform of your truncated random process. So the process is almost the same, except that you take the ensemble average, right? So in deterministic case, you didn't have expectation. And here, this was the Fourier transform of your single signal, but now you have this statistical definition. And here goes the theorem called Wiener-Khinchin theorem, which says that your power spectral density of a random process can be alternatively derived by using what? Fourier transform with respect to tau and time average with respect to t of what? Expectation of x of t plus tau times x of t conjugate. So the difference is that here you just have expectations. Got it? There is no difference. This is why actually in many textbooks they didn't wrong. They were not wrong in the sense that a deterministic signal is a special case of random process where you have what? A single sample path with probability 1. In that case, you don't have expectations. And you have single signal. Then this result is same as what I have been talking to you today's lecture. For deterministic signal, you have power spectrum, you have power spectral density, alternative derivation, something like that. So that's all for the lecture. 이제 문제는 이걸 어떻게 끄냐예요. 마우스가 안 움직이는데. 얘로 하면 되겠네, 그렇죠? 오케이. 뭔가 되는 것 같아요.